Okay, so this week we're going to be talking about the concept of curve fitting. So let me write this up here. And in many ways, you'll probably have some kind of intuitive understanding of curve fitting in general, which is think about collecting data. And curve fitting in some sense is sort of your more introductory way to start thinking about data analysis. Suppose I take some data. Here it is. And you could start looking at this data, and you want to start thinking about the trends that this data represents. The fact of the matter is the data might actually be taken, and there's some errors in measurement of the data. So the question is, do you really believe that there's really all this scatter here? Or is it more important that you just simply get the right trend out of this data set? All data typically has measurement error, and so you could draw error bars on here, even if you know how to quantify those error bars. But the simplest thing you might do, if asked, is to tell, if someone asked you, tell me about this data, you might say, well, look, this data kind of sits on that line. So instead of thinking about the data as being each data point as being so important that you're off this line, but somehow that line conveys all the important things associated with that data set. So you might say, okay, really what I would like to understand is that line. I can write down an equation of a line, there it is. And then the real question comes, which is, how do I pick A and B to sort of get me my best fit line to the data? So that's really what we're going to be talking about, curve fitting. Curve fitting gives you, instead of just an eyeball metric, looking at that thing and trying to get your right line, is how would I actually go about trying to determine these two constants, A and B, that best fits the data? And by the way, what does it mean, best fits the data? This is already problematic because we have to figure out what best means. Okay? All right, so we're going to start introducing this idea in context of this curve fitting idea. So what we can think about is that we have a bunch of data points. x1, y1, x2, y2, so forth, all the way to xn, yn. Okay, so we have n data points. You know, this could be something like what you might have. And what you'd like to do is figure out, through these n given data points, what is, let's say, for instance, the best line that would go through this. Now, if you notice, the line doesn't actually go through most of the points. It goes near them, and it gets you the right trend. And so in some sense, you could say, well, I'm using this line, but for instance, I've made an error. It doesn't go through that point. It goes close to the point. And so you could say there's an error there. So you could start saying that if I want to take this representation of this function, it goes near the point, but with some error. And in fact, what we're going to talk about here then is this going to be my curve, f of x, I'm going to assume. And so when I think about f of x, it goes near the data point, but there is some error associated with it. This here is, in some sense, what I want to try to minimize. I want to try to minimize the error, but not just at that point. I want to minimize the error across the whole entire set of data that I have, all n points. Okay? So that is the objective that we have and the things we want to talk about today in context of data methods, and in particular this idea of curve fitting. What I'll say also about this is that when we think about curve fitting, later on in the class we're going to talk about higher levels of curve fitting or other ways to do data reductions. And if you think about this, one way to think about this line is you're taking all these n points and you're reducing it all down into a two-parameter space, A and B. So what you've done is you've taken an n-dimensional space and you've reduced it down to a two-dimensional space. It's called Dimensionality Reduction. I'm going to cover some of that later on in this class, but I want you to start thinking about one way to start thinking about this error is how do I collapse my data onto something meaningful? Okay? And this is one way to do it. So let's talk about what it means to have a best fit. So I'm going to define, let me erase this here. Let me put this a little bit over here. I want to talk about what we mean by best. So we can have choices about how we define error. And so I'm going to give you some different conceptions about what it means to define an error. So for instance, here's one. We could look at the maximum error. And what you want to do is minimize the maximum error. Well, how do I define the maximum error? It's called the infinity error of the function f. And what I'm looking at is the following. You try to minimize the maximum of the difference of your solution minus the actual data point, absolute value. So here's the data. This function is now evaluated where at the same x values where this data is gathered. And you say, OK, what is the difference? And what I want to do now is make sure that if I look at that maximal error, I want to try to minimize this quantity. So what is this maximal distance? Well, just basically, think about it here. It's my distance from my point down to the line. And I can calculate this distance for every single point. And what I want to do is figure out whichever one is the maximum. I want to try to make this thing be as small as possible. OK? Second, another possible error measure is called the average error, sometimes also called the L1 error. And this is defined as the following. E1 for the L1 f is equal to, here's what you do. You sum over all the points so you take your point minus the data point, so this distance. It's the same like this, but here what it's just saying is find which point has the most error and try to make that minimal. Here you're saying, well, actually, I don't want just one point. I want to take all the points. I want to take all the distances between my guess and the actual position it's in, add them all up, divide by n, and that gives me an average error. Coming back to here, you can see I'm just going to add all these up, right? My distance from my point down to the line, point down to the line. I'm going to add up all these errors. And after I add them all up, I'm going to divide by the total number of points I have. That's going to give me the average length of that vector. And what I want to do is put this line in such a way that that average is minimal. OK? So it's another way to define error. So here's two ways to think about writing down the best fit. There's a third. This is called the root mean square. And it is called, or the L2 error, which is the following. You take, instead of the average, you take the average of the squares. Let me write it down. There it is. So you take not just the distance from where you are to the line, or so from the data to the line. You take that distance, you square it, you sum them all up, all the squares up, you divide by the total number of points, then you take the square root. Okay? So this is something like the Pythagorean theorem idea, which is if I want to find the length of a vector, I take the square of the two sides, square root. Square of all the sides, square root. This looks a lot like the Pythagorean theorem. Okay? So this is a measure. It's called often root mean square or least square error. And this is actually the standard. Most people, when they talk about error, the default, typically when people are talking about it, is this least square fit error. Again, coming back to here, how to think about it. You take your distance and you square them. You square all the distances, divide by n, so it gives you an average square of the distance. square root, and what you try to do is put this line somewhere that minimizes this. So how do we pick a good error measurement, right? So this could work, this could work, this could work. You know, which one would you pick? Well, so everything you would pick, there are strengths and weaknesses. So let's talk about the maximal error right here. So here's my data, but suppose I collected a data point up here. I have all this data, and I collect a data point up here. Well, look at this. The distance from here down to the line is huge. So if I were to do the maximum error, let's color code this in red. If I were to calculate something like this for this kind of data, what it's trying to do is to minimize this maximum. So the line would try to say, look, if I got this big outlier here, it might actually plot that line. Why? Because now your distance is something like this, and the distance to the other points, the maximum distance is somehow minimized in this fit here. Now, of course, when you look at this, you could say, well, that's not a very good fit. Almost all the data is here. It's because that one point. Well, sometimes you can't just throw that point away because you don't like it. And so if you use this maximum error, you can see what it does. It gives you this line as a fit, where clearly the blue line looks a lot better. Then you could say, well, about the average error and the root mean square error? Well, both of them actually do not so badly. Why? Because you have a lot of points here, and you're taking the average. So you're taking this average. So even though this point is very far away, by the time you take the average, this gets averaged out. So you might get the blue curve for the least square fit error, and then you might get something like, you know, for the L1 fit, maybe you get something slightly different. It's not so different there. Let's say that's your L1 fit, and the blue is your L2 fit. So in fact, I give you an example directly in the notes on one of the figures there, figure 3 in the book. It's figure 3.1 that just shows you actually, if you implement these three, you'll see the fit to the data. And what you really get concerned about are this idea of outlier data. Outliers are these points that sit way off of your data set, and they can really mess up some of these measures. If all the data is very nicely clustered, you could use any one of these three, and it really almost doesn't matter. You get very small differences between the A and B. However, if you have an outlier, this gets thrown off severely. So a lot of times people don't use this measure. This measure gets thrown out because it's like, oh, you mean if I have one bad point, I get a really bad fit. Throw it away. These two, more tricky. This one is the standard, but let me make a comment here. Let me come back to drawing data again. If I have a set of data, suppose there it is, and I have an outlier here and an outlier there, what happens? Well, clearly if I use this maximum error, we know that this thing doesn't do very well with outliers, so we'll throw it away. But let's talk about these two. In the root mean square error, what you're going to do is try to draw a curve, and these points, you remember your distance to the curve that you fit, this is squared. So this gets much more heavily influenced in this measure than this one. This one here doesn't square. It just says, oh, that distance, well, it's big, but that's OK. I'll still try to find the right line. Whereas this one here takes this distance, squares it, which makes the situation worse. So for instance, a situation like this, you might actually find that the root mean square gives you this as a curve fit. Why does it give you this? I mean, most of your data sits along here. It's because of these outliers. The L1, however, actually does a pretty good job. The L1 just simply doesn't get thrown off as much by these outliers because you just average over everything. You don't square the difference. OK. The L1 is actually interesting because the L1 is now playing a big role these days in what's called compressive sensing and sparse sensors. And so I'm not going to get into that so much, but this is actually kind of a very interesting measure that you could consider later on. So we won't deal too much more with it. We're just going to stick with this root mean square error. Okay? The root mean square error is actually a pretty nice measure of getting this. And it's kind of the standard, least square fit. You probably, maybe have heard that term. But least square fit comes right from this measurement error. And so we want to work with that. OK. Data, fit the data. All you got to do is try to prescribe what kind of fit you want to do to this thing. All right. So let's talk about this least square fit. All right. So what is our objective? Our objective is to take a set of data, endpoints of it, and to, let's say, for instance, fit a line through it. So here's what we're going to do. We're going to take some function f of x. And what we want to do is take this and fit it through the data, where what we're trying to do is minimize the least square fit error, which I'm going to write down right here. We want minimal error. OK. Finding the minimum of this is equivalent to just finding the minimum of that. Right? I'm going to sum all this up. The n never changes, and the square root's there, but who cares? In other words, if I can look at this inner sum there, that's all I really need to think about. Let's look at that. Let's call that E2, which is k equals 1 to n. If I can find the minimum of that, I found the minimum of the least square fit error. OK, if you learn nothing else from calculus, we keep talking about I want to find a minimum. And if you've had calculus, the whole takeaway message about a derivative is that a derivative being 0 is where you find minimums or maximums. But I can always ask you this. Is there a maximum amount of error here in doing a square fit? Let's come back to this picture here. Is there a maximum amount of error? Well, think about it. I could take my line, and I just keep moving it away from the data, and my error will get bigger and bigger and bigger. There is no maximum data. I can make my error infinity just by simply moving this line further and further away. So there's no maximum error. So the only thing you could potentially have is a minimum error. So right away when I say we're going to try to find a minimum, you should think about some derivative has got to be set to 0. OK? That's the concept you want to have in your mind. When we come back to here, you say, I want to minimize this quantity right here. That means I got to take some derivatives being 0. What have I got to play with? What am I trying to actually use to minimize this? Well, there's only two things I got. I've got A and B. That's it. And if I look at this E2, what I have here is this f of xk, which is A x of k plus b minus y of k squared. I want to minimize this. And the only things I got to play with are A and B, which means if I want to minimize this, some derivatives are going to have to set to 0. In particular, here's what I want. That's calculus. I'm trying to minimize. Well, set the derivatives to 0. And the only thing you can take a derivative with respect to is A and B, because those are the things that you're allowed to vary. These x of k and y of k's are data points. You can't change those. Those are given to you. So this is what you want to do, is set those derivatives to 0. OK? So let's go do these calculations. So if I want to take the derivative with respect to A here, here's a sum here. Well, that's not so hard to do. This thing is squared. You take the 2 down. So what you end up with, right, is you have this sum, k equals 1 to n, 2 a of xk plus b minus y of k, okay, times the derivative on the inside with respect to a, which gives you x of k out of this thing. That is equal to 0. Okay, all I did was apply the chain rule. Bring the 2 down, times this, times the derivative on the inside with respect to a. A only shows up here. That pops out an xk for you. So that's what you get here. Let's now do it with respect to b. Again, it's a sum between k goes to 1. You pull out the 2 again. A of xk plus b minus y of k times the derivative now inside with respect to b. Well, the b only shows up here. It's times 1. So there you go. If I want to minimize this error, then these two conditions hold. Oh, by the way, 2 conditions, 2 unknowns. So it's a 2x2 system of equations that I have to solve for. So let's start collecting terms. So in the first, now the 2 I can just divide out, right? Divide both sides by 2. And so you get is a sum, k equals 1 to n. And this first thing here gives you a x of k squared plus b x of k minus y of k x of k equals 0. The second one, divide the 2 out, and you get a x of k plus b y of k. Oh, sorry, plus b. No y of k there. Minus y of k. Okay, so there we go. We got these. And now what I'm going to do, I've made this comment before in class when we started talking about linear systems. Everything's going to come down to solving linear systems. It's all going to be ax equal to b at the end. This is ax equal to b. It's a 2x2 system of differential equations. And in fact, here it is. The 2 things I don't know, a and b. And what I can do is say, well, look, I can pull the a out of this. And then what I get here in front of a is a sum of xk squareds. And in terms of in front of the b, I just get a sum of xk's. And on the right-hand side, if I take this over, it's the sum of yk xk. That is what this first set of equations says. Remember, if I take this is my ax equal to b. I take this times this times this is equal to this. That's that equation. And by the way, these sums are from 1 to n. I won't write them in here because they'll get too small. Second line says, what's in front of the a? Sum of the x of k's. Then I sum up over all the b's. Sum of 1 through n of b. Well, what does that give you? Well, if you sum up b n times, you get n times b, which all I got to do is put the n there. You're done. Now on the other side, I move the y of k over, sum y of k. Two equations, 2 unknowns. In other words, I just take all my x values that I have in my data set. I square each one, add it together. I take all my x values, just sum them together on the off diagonals, and then n here. So this matrix will be prescribed. It's symmetric. And on the other side, I take all my y of k's, x of k's products, add them together, and all my y of k's. So if I basically build these 2 matrices, to solve it, I can just do a backslash command. It's a 2x2 system, and it gives me back the a and b that minimize the error, and now give me a minimum error here, and so that's going to be my least square fit line. And that's it. That's how you do least square fit lines. It's as simple as that. Remember, what does a derivative do? Finds you a minimum. If you know, that's the only thing you should have really taken out of calculus first quarter, is that derivatives, when they're 0, that's a minimum or a maximum. But what we know here, there is no maximum error. So if I set the derivatives and they're 0, it's got to be a minimum. Because I know there's no, I can make infinite error if I want. The only place I can make a minimum, something that sets this to 0 is if it's a minimum. And I have found the conditions for which A and B basically minimize this error. Okay, so that's it. That is a least square fit line. And those are the formulas. Okay, so by the way, in Matlab, we're going to learn how to work with this. There's going to be some Matlab commands in the third lecture on the curve fitting. We'll talk about basically using Matlab commands that will just do all of this for you, right? And what it essentially does is it says, okay, you want to fit this? This matrix never changes. Like, so what we've done this is the generic formula for a least square fit line for any data. So all you got to do is compute these matrix, this right-hand side, and it gives you A and B. So it's programmed into Matlab, and so you can easily use it. But let's think about some other things we might want to do with this. Because that's just a line fit, and maybe we don't want to fit a line. Maybe we have something a little bit more sophisticated, and we would like to fit something a little more sophisticated. So, for instance, I have my data, and what if my data does this? Well, you know, if I try to do a line fit to that kind of data, I might get something like this. But that doesn't look like a line, does it? Kind of looks more like something you might want to fit this to. Well, something that looks like that might be, in fact, something, the easiest thing to think about is a parabola. Right? You could think about this thing being a parabola. And then the question is, well, what happens now if I try to fit a parabola through the data versus a line? So let's talk about that. So now I'm saying, all right, so now my function, f of x, there it is. And so what I want to do is the same thing I did before. I want to fit this, and I want to minimize the E2 error. So now in this case, here's what I'm trying to minimize. I have the n data points, and now the function I have is ax squared plus bx plus c minus the y of k squared. And I want to minimize this. How do you minimize? You set a derivative to 0. And now, what kind of things do you take derivatives with respect to set this thing to 0? Well, same thing as you did before, except for now, you want to set the derivative with respect to a to be 0. You want to take the derivative with respect to b to be 0, and you want to take the derivative with c to be 0. So what do you get out of this? Each one of these will give you an equation. In other words, there's an equation at which the derivative is 0 for a given a. Or for taking the derivative with respect to a, this will be 0 somewhere, this will be 0, this will be 0. So this is going to be 3 constraints, and you have 3 unknowns, a, b, c. So what you end up with is a 3x3 system of equations. And that 3x3 system of equations are for solving for a, b, c. Okay? And by the way, what do you think is going to happen if we would have tried to fit this not to a parabola, but to a cubic function? Then you'd have ax cubed plus bx squared plus cx plus d. So now you have 4 parameters. Well, you just do this same thing, but you now have a d2 delta d equal to 0. So you have a 4th constraint. So if you have a polynomial fit, whatever the degree of the polynomial is the degree of derivatives you have to take here, set them to 0, and it's going to give you here, if I have a 2nd order polynomial, it gives me a 3x3. If I have an nth order polynomial, it's going to give me an m plus 1 by m plus 1 system of equations to solve for the coefficients. Okay? everything comes back down to solving the linear problem ax equal to b. Okay? So again, this highlights the fact that solving ax equal to b, it shows up everywhere. Everything's going to be about solving. A lot of these problems will be just about solving these such linear systems. And here's how it just shows up in just the simplest example of a data analysis problem where you're trying to do curve fitting. All right, so let's play some tricks with this. Because everything I've showed you so far works because we picked polynomials here. Right? We put functions, power function, functions of the power of x. And in that case, it's very easy to write down these derivatives. And more importantly, if we come over here, if you have a polynomial and you do this, what you end up with is this nice separation into an ax equal to b problem. This is easy. And in fact, like I said, if you have a higher degree polynomial, you just get a 3x3 system, a 4x4 system, a 10x10 system. You can easily separate it out for a polynomial. So polynomials are fine, but the problem is you may not want to use a polynomial for a fit. So let's talk about some other options. Suppose instead that data you have there, you have some belief that actually it might have some kind of exponential behavior. So you'd say my fit here is going to be c e to the ax. This is no longer a polynomial. So now the question is, what does that do for your system of equations? Well, let's go through the process and see what happens. So now this is my fit to the data, no longer polynomial. And remember, what I want to do is minimize this quantity. Oop. It's OK. So I take all my data, and I'm looking at now f of xk minus y of k. Well, this is c e to the a xk minus y of k squared. OK? So that's my error that I'm trying to minimize. So let's do the same procedures we did before. I have two parameters, c and a. And I'm trying to find c and a so that this is the best fit. So to find c and a that it's the best fit, I impose the following, that the derivative with respect to a is 0, and the derivative with respect to c is 0. OK, so what does the first equation look like when you do this? Well, you get this sum, 2 drops down, now times the derivative with respect to a. Well, the a is up here, so it's going to give you back a c e to the a x of k times x of k by your chain rule. And all that's supposed to be equal to 0. Sorry, I ran out of space there. And if you do this with respect to c, you get 2c e to the a x of k minus y of k times the respects with c gives you that back out there. And that's equal to 0. OK, 2 equations, 2 unknowns. Right? So here's an equation, here's an equation. We have 2 unknowns. And if I rewrite this, kind of simplify a little bit, here's what I get. And I'll show you what the problem is. Here's the first equation, if you write it in a little bit more simple form. The second equation comes like this. OK? 2 equations, 2 unknowns. The problem with this is these are nonlinear equations. So you can't write them as ax equal to b. Ax equal to b are linear equations. These are nonlinear equations. So right away, I just took a fairly simple function, right, e to the x. It's a well-known, it's not like I picked something crazy. This is just a very simple function. And yet, right away, what you result with is a 2 by 2 system, which is nonlinear. The problem with nonlinear systems is, one, how many solutions are there? Nonlinear systems can have 1, can have 5, can have infinity, can have 0. You don't know. There's no guarantees about it. And so in this sense, you're kind of in a situation which is very bad because you don't know how many solutions there are to this, and you don't even know a constructive way to follow through to actually get you your solutions. Okay. Now, what I'm going to show you is that at least in this case, for the exponential, you can apply some tricks. You can do what's called data linearization. So this doesn't always work, but there's a few functions which allow you to do this, which allow you to do this data linearization. So let me erase this here and show you how the data linearization works. Let's take the data and do a data linearization. So let's define a new variable y, which is the log of y. So remember, y is my data in the y direction. I have x, y, xi, yi. These are my data sets. So I'm going to take the log of the data instead. Big X is equal to little x. And big B will be log of c. So let's talk then about what I want to do. So remember, now what you have is you're going to try to fit this again with some function y is equal to c e to the ax. Now let's take the log of both sides. So if you take the log of this side, take the log of this side, and what do you get? Well, think about this. Log of y, well, isn't that big Y? So this, on the left now, I have my data is y is equal to, if you remember your log rules, log of a product is log c plus log e to the ax. Okay? Hey, but wait a minute. Log c, then I'm going to call that b. So this is going to be b. What does a log do to an exponential? They cancel each other out. So log of e, a to the x, these two cancel, just gives you ax. So what have I got now? Well, now I have y is equal to, but by the way, this little x now is big X, so I have a big X plus b. Oh, look at that. By doing this transformation of the data, what I really do in this new variables is I can do a linear fit. I know how to solve this. In fact, before I erased this board, maybe I should have kept it up, I actually did the 2 by 2 system, and I showed you what a and b are. All you got to do now is, instead of representing your data directly as little x and little y, you take your data and you keep it as big X and big Y. So you take your x points, they're the same, but the big deal is now you take your y data and you take the natural log of them. And if you do that, now you can do a linear fit. So for those of you who play with something like Excel, Excel has some very standard data fitting tools. So does Matlab, obviously. But even in Excel, you can sort of do line fits, parabolic fits, because it will do all the polynomials for you. But also, Excel will allow you to do exponential fits. Why? It's not because if you come back over here, if you look at the exponential fit, at least if you try to do what we did before, the exponential fit would give you a system of 2 by 2 system of equations that you can't solve. Okay, so that's a problem. But if you do this data linearization trick, then you just go back to solving a line fit. through the log of the data. That's it. So once you solve this, you can actually find big A, big B for the data, and you can go back through this transformation. Y is equal to log y. And so if you exponentiate both sides, you go back the original data set. OK, so this gives you a way to think about fitting data with general polynomials. It gives you a way to think about fitting data with special functions like the exponent function. And there's not actually a lot of this data linearization trick is very special. It really kind of only works for something like exponential fits. But be as it may, exponential fits are a very important class of problems, and so it works quite well for there. And so you can do some stuff with that. OK, so let's finish this off with just making sure we have the big picture thinking right. OK, here are the key ideas. I have a function. And I want to fit this function to my data. And I'm going to try to fit some kind of function that's actually parameterized by a bunch of parameters. In this case, this was like ax equal to b. The a and the b were two parameters. And here you say, I'm going to try to go pick a function. And this function is going to have certain parameters in it that I don't know what they are. But my point is to try to figure out what C1, C2, all the way to Cm are, such that when I apply that fit, it gives me the best fit in a least square fit way. So then my error that I have to minimize, well, it's equal to the sum of the function that I have minus the actual data points squared. Right? So I take my fit to the data with all these things. And what I want to do is minimize this. So all I got to do to find that is to set the derivative of this thing here to 0 for j equals 1, 2, all the way to m, because I have m parameters. OK? So this works. And in fact, when you do this, what's going to happen is you're going to have 2 coming down. So let's go ahead and apply this here. If I apply this result here, I'm going to get the 2 is going to come down. So I'm going to get a sum 2. We get back this thing f of x, c1, c2, all the way to c of m minus y of k, times the derivative now with respect to c of j, which is now df dc of j. That's equal to 0. And this is, I get m of these. Right? So I do this for all m parameters. And what does it give me? It gives me m equations for the m unknowns. The problem with this general formula is that if this is a fairly complicated function, it's nonlinear. So part of what we want to try to understand is how do I actually do nonlinear fits? And we're going to actually work on a technique in the third lecture of the data fitting that allows me to do more general things that have a nonlinear function of this sort. Ultimately, what this is some kind of optimization problem. Minimization can be associated with optimization. And we'd like to find solutions to this, because if you can, then you can fit it with whatever function you would like. Not just polynomials, not just the exponent. It is important that we are allowed to do something a little bit more sophisticated than just polynomials and exponentials. And so this gives us a way to do it. Just the problem is nonlinear set of equations that come out of this thing. So with that, we'll stop here for the first lecture.